Powerful earthquakes rarely arrive in pairs. Even more unusual is a sequence in which one massive rupture is followed almost immediately by another, even larger event. Within only 39 seconds, two major earthquakes struck northern Venezuela near the town of Yumare, producing one of the most remarkable seismic sequences recorded in the Caribbean region in modern history. The first measured magnitude 7.2, before emergency agencies and seismic monitoring centers had even completed their first automatic calculations. A second earthquake, measuring magnitude 7.5, had already begun. This event has drawn attention across South America, particularly because strong shaking was reported far beyond Venezuela, reaching neighboring countries including Brazil. That has led many people to ask an understandable question. Why would earthquakes centered in Venezuela be described as shaking Brazil? The answer lies in the enormous amount of energy released by earthquakes of this size. Large seismic waves do not recognize political borders. Instead, they travel through vast sections of the Earth's crust, allowing shaking to be felt hundreds of miles or hundreds of kilometers away from the rupture itself. For many residents across northern South America, this sequence served as a reminder that major earthquakes can affect entire regions rather than a single nation. The sequence began at approximately 22 hours, 4 minutes, and 33 seconds, Coordinated Universal Time, on the 24th of June, 2026. The epicenter of the first earthquake was located southeast of Yumare in north-central Venezuela at a depth of approximately 12.5 miles, or 20.3 kilometers. At first glance, a magnitude 7.2 earthquake would normally be considered the principal event of any seismic crisis. In many parts of the world, such an earthquake would stand as the largest earthquake recorded in years. Instead, it became the opening act. Only 39 seconds later, at approximately 22 hours, 5 minutes, and 11 seconds, Coordinated Universal Time, a second rupture occurred nearby. This earthquake measured magnitude 7.5 and originated even closer to the Earth's surface at a depth of approximately 6.25 miles, or 10 kilometers. Because it released significantly more energy than the preceding earthquake, seismologists classified the earlier magnitude 7.2 event as a foreshock, while recognizing the second earthquake as the mainshock. This sequence is known as a seismic doublet. Unlike ordinary earthquake sequences, where a major earthquake is followed by numerous smaller aftershocks over hours, days, or months, a doublet involves two earthquakes of comparable size occurring almost back-to-back within the same region. These events are uncommon because they require a very specific chain of geological conditions. One rupture must rapidly alter stresses within nearby sections of the Earth's crust, bringing an adjacent fault segment to the point of failure almost immediately. Rather than allowing stress to dissipate gradually, the first earthquake effectively transfers enough strain to trigger another major rupture before the crust has time to stabilize. That appears to be exactly what unfolded near Yumare. Although earthquake maps often display earthquakes as single dots, those dots can create a misleading impression. A magnitude 7.5 earthquake does not originate from one tiny location beneath the surface. Instead, it represents movement along a substantial portion of a fault. Strike-slip earthquakes of this magnitude commonly rupture fault zones stretching approximately 93 miles in length and about 12.5 miles in width, equivalent to roughly 150 kilometers by 20 kilometers. Within that large zone, enormous blocks of rock suddenly slide past one another after accumulating stress over decades or even centuries. The timing of this sequence strongly suggests that the two earthquakes were mechanically connected. Rather than representing unrelated events occurring by coincidence, both earthquakes likely formed part of the same evolving rupture process. As the first fault segment slipped, stress concentrations rapidly increased on neighboring sections of the fault system. Within less than 1 minute, another large section reached its breaking point, unleashing an even larger earthquake. This type of cascading failure demonstrates that earthquake ruptures are not always isolated events. Under the right geological conditions, one rupture can immediately influence another. Understanding why this happened requires examining the remarkable tectonic setting of northern Venezuela. The earthquakes occurred near coordinates approximately 10 and 4/10 degrees north latitude and 68 and 1/2 degrees west longitude, placing the rupture within one of the most active plate boundary regions in northern South America. Far from being located within the stable interior of a tectonic plate, this region marks the boundary where the Caribbean plate gradually slides eastward relative to the South American plate. That movement occurs at a rate of roughly 3/4 of an inch each year, or about 20 millimeters annually. Such motion may sound insignificant when measured over a single year, yet geological time transforms small annual movements into enormous accumulations of strain. Every passing decade adds additional stress. Every passing century stores still more elastic energy within the surrounding rocks. Eventually, the accumulated strain exceeds the strength of the fault itself. At that moment, the rocks no longer bend. They break, releasing decades or centuries of stored energy in only seconds. Unlike plate boundaries dominated by head-on collisions, northern Venezuela occupies what geologists describe as a transform or strike-slip environment. Here, the two tectonic plates primarily slide horizontally past one another. The movement resembles two enormous slabs of rough stone being forced sideways along their shared boundary. Friction prevents continuous motion. Instead, the rocks lock together while tectonic forces continue pushing from opposite directions. Stress accumulates silently beneath the surface until the resistance is overcome, allowing sudden movement that produces an earthquake. This style of faulting bears a strong resemblance to California's famous San Andreas Fault. Both are right lateral strike slip systems. In practical terms, standing on one side of the fault and looking across it, the opposite side would appear to move toward the right during rupture. Although separated by thousands of miles and operating within different tectonic settings, both systems demonstrate the same fundamental mechanism of horizontal crustal displacement. The most likely source of the June 24th sequence is the San Sebastián Fault, one of the principal faults accommodating motion between the Caribbean and South American plates. Extending for more than 186 miles, or over 300 kilometers, this major strike-slip fault follows much of Venezuela's north-central coastline before linking with other active fault systems across the region. Its long history reveals that it is fully capable of producing earthquakes reaching magnitude 7 and above. The shallow depth of the magnitude 7.5 earthquake strongly supports this interpretation. Earthquakes associated with major continental strike-slip faults commonly originate within the upper portion of the Earth's crust, where rocks remain sufficiently brittle to fracture suddenly. A hypocenter only about 6 1/4 miles, or 10 kilometers, beneath the surface fits well within the expected depth range for large transform fault earthquakes. Yet the geology surrounding Yumare is more complicated than a single isolated fault. The epicentral region sits close to an intricate network of interconnected structures, collectively known as the Bocano, San Sebastián, El Pilar fault system. Rather than consisting of one continuous fracture slicing cleanly across the landscape, this plate boundary resembles a network of overlapping and branching faults, sharing the burden of accommodating plate motion across northern Venezuela. One of the most important members of this system is the Bocano Fault. Running generally northeast to southwest along the Venezuelan Andes, it extends through the Yaracuy Valley not far from Yumare before connecting with neighboring fault structures. It has played a central role in shaping the mountains, valleys, and drainage patterns of western Venezuela over millions of years. Geological evidence indicates that this fault has generated numerous significant earthquakes throughout its history, demonstrating its continued activity as part of the regional plate boundary. Nearby lies the La Victoria Fault, another significant strike-slip structure participating in the overall deformation zone. Although current evidence points most strongly toward the San Sebastián Fault as the principal source of the June 24th earthquakes, the close proximity of multiple interconnected faults raises an intriguing possibility. The rupture may not have remained confined to a single fault segment. Instead, The first earthquake may have transferred stress into adjacent segments or nearby splays, helping initiate the second and larger rupture only 39 seconds later. Such behavior illustrates why complex fault systems present some of the greatest challenges in earthquake science. The Earth's crust does not always fail along neat, uninterrupted lines. Instead, stress may jump across bends, stepovers, intersections, or linked fault branches, producing earthquake sequences far more complicated than a single rupture alone. The June 24th seismic doublet stands as a striking example of that complexity, demonstrating that the interaction between neighboring faults can transform one powerful earthquake into two of the strongest earthquakes the region has experienced in modern times. The geological complexity of northern Venezuela extends well beyond the faults visible on geological maps. The entire region represents the surface expression of a plate boundary stretching for nearly 800 miles, or approximately 1,300 kilometers, across the northern edge of South America. Instead of being concentrated along one perfectly defined fracture, the motion between the Caribbean plate and the South American plate is distributed across several major strike-slip faults that together absorb the steady eastward movement of the Caribbean plate. Every year, the plates continue to shift by roughly 3/4 of an inch, or about 20 millimeters. Although that movement appears almost imperceptible during a human lifetime, it steadily stores enormous quantities of elastic strain within the crust. That accumulated strain explains why earthquakes sometimes arrive after decades of relative quiet. Rocks deep beneath the surface behave much like a compressed spring. As tectonic forces continue acting upon them, they deform slowly while remaining locked together by friction. Once the stored stress exceeds the strength of the fault, the rocks abruptly slip into a new position. The movement may last only several seconds, but it releases energy that had been accumulating over many generations. The June 24 sequence demonstrated this process with remarkable clarity. Rather than one isolated rupture relieving all of the accumulated stress, two neighboring ruptures occurred almost back-to-back. The first magnitude 7.2 earthquake altered the stress field surrounding the fault system almost instantly. In many earthquake sequences, this redistribution of stress produces aftershocks that are noticeably smaller than the original event. In this case, however, the stress changes appear to have been sufficient to bring another large section of the fault system to failure almost immediately. This phenomenon illustrates one of the most challenging aspects of earthquake behavior. Faults rarely exist in complete isolation. Instead, they interact with neighboring structures through changes in stress. When one section slips, nearby faults may either become more stable or move closer to failure depending upon their orientation and the direction of movement. In northern Venezuela, where several active strike-slip faults converge within a relatively narrow corridor, these interactions become especially significant. The proximity of the San Sebastián Fault, the Boconó Fault, the La Victoria Fault, and several offshore fault splays creates a complicated network through which tectonic stresses are continuously redistributed. Although the principal rupture most likely occurred along the San Sebastián Fault, the unusual timing of the doublet raises the possibility that rupture propagated between adjacent fault segments rather than remaining confined to one continuous break. Such cascading behavior is uncommon, but entirely consistent with the mechanics of interconnected transform fault systems. Earthquake locations displayed on maps often conceal another important reality. The published epicenter represents only the point where rupture began, not the full area over which the fault actually slipped. For an earthquake measuring magnitude 7.5, the rupture typically extends across a fault surface roughly 93 miles long and approximately 12.5 miles wide, equivalent to about 150 kilometers by 20 kilometers. Within that area, rocks on opposite sides of the fault may move several feet or more than 1 meter relative to one another during only a few seconds. Such movement permanently changes the position of the Earth's crust. Roads, pipelines, buried utilities, and natural drainage systems crossing the fault can all experience displacement. Even where the rupture does not reach the surface, the intense seismic waves generated by rapid fault movement travel outward through surrounding rock in every direction. Those seismic waves explain why reports of shaking extended far beyond Venezuela. Residents across northern Colombia, portions of the Caribbean, Guyana, and northern Brazil experienced varying degrees of motion despite being located considerable distances from the epicenter. Large earthquakes generate several different categories of seismic waves, each behaving differently as they travel through the earth. Primary waves travel the fastest, compressing and expanding the rocks through which they pass. Secondary waves arrive afterward, moving the ground in a side-to-side or up-and-down motion. Finally, surface waves travel along the Earth's exterior and often produce the longest-lasting and most noticeable shaking for people located far from the epicenter. Because earthquakes of magnitude 7 and above release extraordinary amounts of energy, these waves can propagate across vast portions of an entire continent before gradually losing strength. This explains why the event attracted attention across Brazil, despite occurring inside Venezuelan territory. Modern national borders have little relevance to seismic energy. Once released, earthquake waves simply follow the physical properties of the rocks through which they travel. In stable portions of continental crust, especially across parts of South America, shaking from very large earthquakes can remain detectable hundreds of miles or hundreds of kilometers from the source. Another factor contributing to the widespread effects was the shallow depth of the mainshock. Originating only about 6¼ miles or 10 kilometers beneath the surface, much of its energy reached populated areas before being significantly absorbed by deeper rock layers. In general, shallow earthquakes tend to produce stronger ground motion near the epicenter than earthquakes of comparable magnitude occurring much deeper within the Earth. Northern Venezuela has experienced this pattern repeatedly throughout recorded history. Although the immediate region surrounding the June 24 earthquakes has experienced relatively few magnitude 6 or larger earthquakes during the past century, the broader plate boundary has repeatedly demonstrated its capacity to produce destructive seismic events. Only months before the June 24 sequence, another notable earthquake doublet struck farther west during September of the previous year. That earlier sequence consisted of a magnitude 6.2 earthquake followed closely by a magnitude 6.3 event. Although significantly smaller than the June 24 earthquakes, the earlier doublet caused fatalities, injured well over 100 people, and resulted in widespread structural damage across parts of Zulia and Lara. The occurrence of two separate doublet sequences within less than 1 year serves as another reminder that the northern Venezuelan plate boundary remains an active and evolving tectonic environment. Historical records reveal additional examples of damaging earthquakes across the region. During September of 2009, a magnitude 6.4 earthquake struck near Moron, damaging buildings and injuring numerous residents. 2 decades earlier, a magnitude 6.0 earthquake produced structural damage around Valencia. In the mid-1970s, another magnitude 6 class earthquake affected western Venezuela, again reflecting the ongoing release of tectonic stress along the plate boundary. Perhaps the most widely remembered earthquake in modern Venezuelan history occurred during July of 1967. Centered east of the June 24 epicenter near Caracas, that magnitude 6.6 earthquake produced devastating consequences. Hundreds of people lost their lives, many more sustained injuries, and numerous apartment buildings collapsed. The disaster transformed public awareness of seismic risk throughout Venezuela and remains one of the country's defining natural disasters of the 20th century. When viewed together, these earthquakes reveal a recurring pattern rather than isolated incidents. The Caribbean plate has not stopped moving, nor has the South American plate changed direction. The forces responsible for previous earthquakes remain active today, continuing to load stress onto the same interconnected network of strike-slip faults extending across northern Venezuela. Over more than 100 years of instrumental observations, only a handful of earthquakes exceeding magnitude 7 have occurred within northern Venezuela or immediately offshore. That relatively small number reflects their rarity rather than any absence of tectonic activity. Major plate boundary faults often remain locked for extended periods before releasing decades or centuries of accumulated strain during a single large rupture. The June 24 earthquakes, therefore, occupy a particularly significant place in the modern seismic history of northern South America. Beyond their individual magnitudes, the extraordinary feature lies in their timing. Two earthquakes powerful enough to rank among the region's largest events occurred less than 1 minute apart. That sequence highlights the dynamic relationship between neighboring fault segments and demonstrates that the release of tectonic stress is not always confined to a single rupture. Instead, under the right geological conditions, one major earthquake may immediately influence another, producing a chain of events that unfolds in seconds, while representing the culmination of forces that have been building beneath northern Venezuela for countless generations.